participants. So, Professor Mudli completed his PhD in signal processing from the Department of Electrical Engineering at Indian Institute of Technology, Kharagpur in 2019. So since 2020, he is working as a faculty member in the Department of Electronics and Engineering at IIT BHU. Professor Mudli received the National Postdoctoral Fellowship from ACRB India in 2020. He is a silver medalist from NIT Rourkela. The broad research areas of Dr. Mudli are biomedical instrumentation and measurements, signal and image processing, Internet of Things, and deep learning. Recently, he has received the Outstanding Reviewer Award from IEEE I&M Society in 2019. He is the recipient of IEEE Uttar Pradesh Section Young Professional Star Award 2021. Currently, he is serving as an associate editor of IEEE Transactions on Instrumentation and Measurement and reviewer of several other IEEE journals. So with this, I now request you to kindly start your session and share your expertise with us, sir.
Thank you, Dr. Deepak, for the nice introduction. So I hope this is the second session of today's evening. Yes. So let me share the screen with you. Yeah. Is it
It's
visible
visible,
now?
sir. Yeah,
Yeah.
it's visible, sir.
Okay. So, good afternoon to everyone. I'm Dr. Mudli, and this is my research topic that I have mentioned here. Today, I'll be talking about machine learning for signal and image processing. And here is my affiliation and email ID and contact number. You can contact me anytime for any research collaboration or any kind of technical interaction. So let's start with this session. Yeah. So here is the outline of this session. I'll be talking about AI ML for signal processing. Then we'll briefly introduce about convex optimization techniques. Then convex optimization tools. I'll introduce you with some of the very elegant and powerful, mathematical tools which are widely used in ML or AI background, right? So those algorithms runs in the background, and you can utilize it for specific applications, or you can customize your algorithms instead of using those AI tools as a black box, right? So that's how we'll proceed. So mostly in this talk, what I have focused, since most of you are from computer science background, so and I am from actually electronics background. So mostly in throughout the talk, I'll be mostly focusing on the the mathematical background behind all these AI ML tools, fusing the signal processing concepts there, including the feature extraction and yeah, many pre-processing steps, how people do it, and what are the state of the art algorithms available with I'll introduce you all of you with that with some of the new tools, so that my goal is to not to use the AI or ML or DL or NN tools as black box. Okay, we'll start exploring them mathematically, and we'll understand how they perform or how to tune their performance, like how to optimize the cost function, objective functions, all these things we'll study. Okay, so therefore we need to understand the in-depth concepts, and that I'll briefly cover in this talk due to limitation of time. I may skip some of these slides, and definitely please let me know if you have any queries in between, or in the end also we can have a small discussion. Okay, so let's understand what do you mean by AI, ML, say neural network or deep learning. So as you can see in this diagram, so AI is the superset. Within that you have ML, then NN, then deep learning. Okay, so whenever we talk about deep learning, many times people get confused how much deep. Okay, So essentially, these are essentially neural networks, right? Immense neural networks. Usually, there are more than say three hidden layers. You have the input layer, output layer. In between, you have hidden layer. If you have more than three hidden layers, those kind of networks are considered deep learning networks. So each one are having some specific applications. Okay, and people over the time people learned all these tools, and they started using these tools as a black box initially. Then as a researcher, if you are a research scholar, or as a faculty member also, many of you have been using all these tools, but I'm not sure whether you have explored it thoroughly, or you have gone through the background of it or not. Okay, so we'll briefly cover all these, mathematical background here in this talk. Okay. So there are plenty of algorithms available under this AI umbrella, like NLP, like intelligent robots, knowledge representation, and under machine learning also you have this logistic regression, linear regression, K-mean, SBM, PCA. So many tools are available, and deep learning also. Most of you are most of you are also using the CNN, RNN, GAN, generative adversarial network, or DVN. All these tools are also quite familiar with you. Okay, so I'm not going to discuss all individual algorithms, since these are very very famous algorithms, and not new exactly, but they have some applications. So far people have been using it, right, for a different application by fusing different tools, or they are trying to develop some hybrid models to solve their purpose. Okay, so what I'll do, like as you understand, like image, it's a in 2D, right? So like it has two dimensions, spatial dimension, right? So it's a kind of signal. You can say signal means it could be one dimensional signal, like the it could have a single independent variable could be there, right? Say time axis, or say frequency axis, or any kind of independent variable, one dimensional signal, like biomedical signals, or any kind of practical signals that you acquire, single channel signal. Those are essentially time series data. Those are 1D signals, right? But when you have, say, spatial domain signals, like you have the coordinates, you have pixel values, you have gray levels. So those are also essentially some kind of signal, but those are in 2D. Similarly, video also, video signals, those are in 3D, right? Frames are there. Another time axis is associated with the spatial coordinates. So likewise, there are multi-dimensional signals, and if you understand how they are being implemented for say 1D, like that can be extended to 2D or higher dimensions. That's the basic goal or the underlying theory that I'm going to cover here, right? Because when a CNN was actually introduced, it was 2D CNN. If you remember, initially it was for image processing applications. So it was actually in 2D. So then 1D CNN came into picture, and people started utilizing it for different applications, 1D or time series, classification or some kind of processing. So okay. So let's understand what are the minimal requirements, like required subjects that you should have for this AI algorithms. Whenever you are talking about AI algorithms development, so there are so many prerequisites are actually available, right? Like you should know the statistics probability, you should have some idea about real analysis, complex analysis, numerical computation, convex optimization. Similarly, you should know about calculus, right? Then you have this loss function. Okay, mostly we talk about some kind of loss function, right? Objective functions. Like so many dimensions you have to cover. Really, it's scary. Like if someone starts from the scratch, starts learning the AI algorithm, so he might get panic by seeing all these dimensions, right? think let's see about this video. My signal is not good here. Okay, nice. Okay, okay. So so in this talk, mostly I'll I'll be speaking about this numerical computation or convex optimization part, which work as a backbone of all the AI/ML algorithms. Whatever AI/ML algorithms currently people are using. So if you go to the uh, theoretical background, you'll understand there is something, some optimization is happening there actually. Okay. And there is a loss function or objective functions involved in that. You try to minimize it iteratively by using different optimizers, right? So mostly, if you remember, people are using this ADAM optimizer, adaptive moment estimation, or say RMS prop, or some kind of gradient descent or stochastic gradient, different optimizer they are using to optimize the parameters that is running in the background, right? So that aspect of the AI algorithms we will cover in this talk. Okay. So what is the role of optimization in engineering? So it essentially a link between the science and engineering. Actually, optimizers or optimization techniques are not only limited to engineering, so it's also extended to different applications in science, including signal processing, communications, right? So it has touched almost all the domains of engineering. So what is so fascinating about this? So what? Sorry. So what is so interesting thing about this optimization? Let's understand. I'll quickly go through the mathematical background, and if required, we'll skip some of the slides. But I'll request everyone just note down some of the keywords. Okay, so because it's very difficult to remember to understand each concept in details. So therefore, while I'm going through different concepts, you can note down some of the keywords or the method, so that later on you can Google it or you can understand in details, because everything is nowadays everything is available online, right? Or if you have any queries also, you can send me email. We can have a discussion. So basically, the optimization problem, if you see, essentially we try to minimize or maximize something, right? You have some cost function, we call it sometimes loss function or objective function. We try to minimize it, right, or maximize it, subjected to some constant is that. Okay, so essentially these constants essentially guide our solution. Okay, the solution will not go out of your requirement or the feasible optimal solution set, right? So the problem here is that when you solve this kind of problem or loss function or cost function, when you try to minimize, many times it may not be convex, right? So I'll come to the concept of convex or non-convex. So nowadays, if you see like logarithm function or many kind of entropy, cross entropy, all these loss functions, those are actually not purely convex functions, right? So they are we face many difficulty, meaning that the solution may get stuck at some local optima, or the computational complexity could be very large actually. Okay, so therefore, what we can do, like we can go for some kind of convex optimization tools also, or we can frame our problem in a convex optimization framework, right? So what advantage we get? Essentially, when you try to solve a convex optimization problem, it gives you some kind of guarantee of feasibility, right? Or infeasibility. It will tell you there are certain tools available that will tell you if the problem has a closed form solution or not, right? So there are plenty of algorithms available also. So that can be utilized to solve a convex optimization problem, and you will mostly get a global optima. That's the beauty of convex optimization. And before the introduction of this deep learning, machine learning tools, people used to have all these signal processing algorithms. They use or computer vision algorithms. They essentially rely on that, which are basically based on pure convex optimization algorithms, and they used to have very good results. But gradually over the time, what happened actually, people could not understand the system. Actually, they could not understand how the input is converted to the output. they give some input to the system and they get some output, but they fail to find a mathematical relation between the input and the output. That was the major, issue they discovered. So therefore, like all these machine learning, deep learning, whatever AI concepts that you study now, so all these concepts came into picture. Okay, those concepts dominated the traditional signal processing. Okay, so that's how the evolution of AI ML tools or machine learning came into picture. So here you can see in the slide, this is a surface or some kind of feasible set, which is actually convex. Okay, convex set. I'm showing you some pictorial representation so that you'll understand how does it look like actually. Okay, so in a objective function, many times you use L2 norm, right? L2 norm is kind of least square problem, right? Quadratic least square problem. Say y minus ax norm 2 square, something like this, right? L2 norm. That if you plot it actually in hyperdimension, it will look like a ball, right? It will look like a ball or globe, right? Similarly, if you use a L1 ball or L1 norm, that's the absolute norm. When you try to minimize the error using absolute value error, so that case that will look like some kind of a pointy rhombus or maybe some kind of square shape, right? So each one loss function and cost function has some shape, right? When you plot it in hyperdimension or in 2D also, you can see it. So I'm showing the similar kind of thing here, just to give you some idea how does the function look like. Okay. So there are, certain definition of convexity. So if you have a function, like practically if you have some problem, you want to minimize it, maximize it, some error function you have formulated. So how do you understand that it's a convex? Okay. So there are certain, theories there. You can see it. Like if you have a function, let's say this is the function, this curve that you see, it's a function, right? So if you take any point here, let's say x point here at this corner, y point here at this corner, and theta, let theta one variable which lies between 0 to 1. Okay. So if you put theta x plus 1 minus theta y, that's actually the line connecting the 2 points x and y, right? So if you put theta equal to 0 here, actually, you will land at this f of y here at this right side corner point, right? If you put theta equal to 1, you will get f of x because this part will be 0, right? You will land at this point. So that's how this, you know, this by varying the value of theta, you will oscillate between these 2 points, x and y. Okay, so that is if the functional value or the chord lies below the line connecting these two. Okay, so that means it's a convex function, right? Otherwise, it's a concave function. So this, convex, concave, convexity, all these things you need not to verify manually. So many toolboxes are available already, right? So we'll see. Similarly, if a function f of x is differentiable, you can also check it. Like this is a first order condition. Okay, this is a first order condition, and right hand side you can see the terms written. That's a first order Taylor series expansion. Okay, at a point x naught. What it says that the function is always an the Taylor series expansion of a function f of x at a point x naught is a is always an underestimator of the function actually. Okay. So these are some maths I am talking about. I'm not sure whether you have studied these things or not. There is a very beautiful book written by Professor Boyd, Stephen Boyd from Stanford University. Okay, so he has written this book, Convex Optimization. So you can go through it. You'll get plenty of algorithms or some new concepts actually there. Okay, which can be also incorporated in your AI ML toolbox, which is still people are exploring that actually. Okay, so this is how the convex optimization problem looks like. As I have already mentioned, you want to minimize or maximize some objective function subjected to some constants are there. Okay, so essentially, how to optimize something? You have some function is there, right? So the basic way of solving the problem is that you try to differentiate it, right? You take the differentiation of that, equate it to 0, then you find the x values, okay? and but the x values could be at some saddle point, right? There could be some saddle points where like the x values could be zero, right? Could be some flat surfaces where there is no shifting or there is no gradient there, right? So if like the standard process, right? So if del f of x equal to zero, if we change x very little at such point, those are called saddle points or flat points. Okay. And positive derivative means you say that f of x is increasing at x, and negative means you understand that it's decreasing function, right? So derivative based solutions are there. Still, if you see the stiffest descent algorithm, right? The the back propagation that you do to optimize all these weights of a neural network. Okay, so they also sometimes follow this gradient based method, right? So it's not an obsolete method. People are still using. Yeah, if you have a multivariate functions also, you can go on differentiating the function with respect to dimension also. So these are some of the basics. I think this gradient descent, most of you know, right? Gradient descent is a very elegant algorithm for solving or to minimize the cost function or loss function. So how does it work actually? If the loss function looks something like this red curve you can see, it starts with some point here, okay, any arbitrary point here, initial values. Then just try to imagine this is like a bowl, right? If you have a bowl and you hold uh, hold a ball at some top corner, just release it smoothly, right? Just release it. It will come down. Okay, it will cross the minima. Okay, global minima. Again, it will go to the next peak maybe. Again, it will come down, right? So it will follow an oscillatory kind of motion, right? That's how this gradient descent works, right? So the descent or it moves in the negative direction of the gradient, right? So and the learning happens in that way. You can decrease the values, okay, in that way, okay, to get to a point where you have a global minima. That's how it works. But if there are certain multiple global minimas or multiple minimas are there, so you may get stuck at some local minima. That was one of the limitations, but people found out some ways to get rid of this local minima problem, right? So you have stochastic gradient descent problems, you have ADA grad, you have RMS prop, okay? You have ADAM algorithm, which combines the concept of momentum, right? So that's how you overcome those limitations of gradient descent. But gradient descent is a very well defined mathematically proven algorithm or method to get all the weights updated. And I'll introduce you with some of the toolbox. Like you can see, you have a CVX toolbox, Convex Optimization Toolbox, provided by Stanford University. If you are using MATLAB, you can follow the setup. So they have already provided the instructions how to, you know, put everything in your path, right? And how to solve any kind of optimization problem. This is a very standard process you have to follow. So and it's a very standard and well defined framework you can follow to solve any optimization problem there, right? Just to check whether it's a feasible or non-feasible or solvable or non-solvable, okay, or whether you can get on global optima, those feasibility you can test there. And also you have a civic spy toolbox, okay, that uses Python, and you can install it using this pp install cvxpy, and you can import the packages, and you can follow the standard steps to run your algorithm also there. Okay, so where do you apply these optimization methods? So far we covered so many types of basic background theory, but where do you apply actually? So these algorithms actually can be applied to many domains actually, many domains of engineering. In the sense, it can be applied to simple one-dimensional signal time series data. It can be applied to images, right? Images means it could be multi modality images also, not only spatial domain. Okay, different modality images can be also processed using the this kind of method, right? So people actually develop all the algorithms that you study. They develop all the algorithms. The background theory is always involving some kind of unbased optimization or some kind of optimization technique. So I'll cover one by one some of the concepts. If you are interested, you can note down. Okay. So here we'll be talking about sparse sensing. Okay, this is a very interesting topic, sometimes known as compressed sensing. The idea was evolved around maybe 2013-14 time, but gradually people started using this idea in almost all the domains of engineering, and they obtain very good result. Okay, so what is the idea here is that you have to, you know, utilize the sparsity of the signal. Okay, whenever I say sparsity of the signal, meaning that the signal has some significant values at some point or location in the spatial domain, or let's say an image in the spatial domain or space, frequency domain also. There will be very significant components, very few significant components, and most of the components of that signal or image will be null or zero, right? For example, if there is a wall, let's imagine that there is a wall, right? A white wall, and you kind of draw a small point at the middle, right? Take an image of that wall. So definitely point is there. When you take the Fourier transform of that, you can see majority of the data actually that is uniform, right? Wall is uniform. So those are having no change in the frequency, or high frequency components will not be there except at the middle point, that different color that you have put, right? So that means those kind of signals are sparse, meaning that you have lots of redundant information. Very few information are significant. Okay, so if you can utilize this sparsity concept or the significant components of the signal, if you can extract and process it in some domain, so your computational complexity can be also drastically reduced, right? So that's how people work, right? So I'll show you some of the examples. Here you can see this is a signal. I'm showing you a time series signal. This is a mixture of say 10 hertz and 60 hertz, right? You have amplitude, you have time here. When you this signal is not actually sparse signal, meaning that at any instance of time you see there is some amplitude values, right? So therefore, this signal is not sparse. Okay. So when you go to the frequency domain of the signal using say Fourier transform, okay, you can see there are multiple spikes here. Very that depend the number of spikes depends upon the frequency components, dominant frequency components, right? So this signal is sparse. Here you can see all the components are zero, and very few components, significance or dominant components are rising here, right? So if you can process the data, image or audio or say any kind of signal processing, any kind of signal, okay, 1D or 2D or 3D, if you can process it in this domain, your computational complexity can be drastically reduced. Okay, so there were actually a large number of algorithms or methods people developed on this compressed testing and sparse testing theory. So what they used to do actually, they instead of sensing the whole bunch of information, for example, a satellite imaging, you are doing some kind of satellite imaging, taking the image of Earth, okay. So if you the megapixel or say there could be the image resolution will be quite large actually, okay, hyperspectral imaging, the resolution will be very large. So if the processing of the data obviously will load the system, right? You have limited hardware, so you have limited power consumption. So what they do actually, essentially, they try to compress it, right? They use standard, say, some kind of JPEG algorithm or some kind of compression algorithm. So as all of you know that compression algorithms works on the principle of redundancy, right? So if you have some redundancy, that can be removed and you can utilize it to compress your data, right? So that's how in other sense, if you can utilize the sparsity of the signal, or the if you can explore the significant component of the signal, so that is the another achievement actually. Similarly, you can represent the signals in sparse domain using the standard, matrix vector multiplication. For example, you have a 1D signal of which something like this time series data, right? It's varying continuously. There are multiple flat surfaces and certain spikes are also there. This signal, if you simply multiply by a first order difference matrix, where we have the diagonal elements -1 here, and the off diagonal elements are zero. Actually, when you multiply this 1D signal with this one, you'll get a consecutive difference between the elements, right? That means when you take the consecutive difference between the elements are the spikes where the signal is rising sharply, so there you get a spike here, right? But at the flat surface, when you take the consecutive difference of the elements of the signal, you'll get a zero. Okay, there is no transition happening there. So that's how this signal is represented in sparse domain. The same thing you know, goes with the image also when you do the image processing, because there is a concept of total variation denoising. I hope some of you have might have used this TVD concept, right? So there also, that also utilize this first order difference matrix and L1 norm, and they try to extract some of the or preserve some of the high frequency component of the signal, meaning that this sudden transition of the signals or the high frequency components of the signal can be preserved, which is very essential in many applications actually. Okay, many practical applications. Simply, if you use a filter, standard frequency domain filter, it may smear your data, right? Let's say lots of edges are there, high frequency components are there. You want to smoothen some of the noisy components, low frequency components. Uh, I mean, you want to remove some of the low frequency components. However, that may affect your high frequency components. So high frequency components are also will be smoothened, right? Over smoothened may happen, right? Therefore, we can develop some of the non linear filters. Okay, so one of the nonlinear filter is called HP filtering, Hadrick Prescott filter, right? So this filter that you can see, I'm just showing you the mathematical background, which is or mathematical objective function. Okay, you can see this is a quadratic function, right? Y minus x norm to square. This is a quadratic function, and the this part right hand side, it's a actually second order difference matrix multiplied with a vector. You can see here, right? I have shown you the second order difference matrix where you have 1 minus 2 1 on the main diamond, all other elements are zero. When you multiply any 1D signal with this one, definitely you get this kind of expression, right? So they solve this problem, optimization problem. This is a very standard convex optimization problem. They solve it and they got a closed form solution of that, right? So simply one step result you will obtain just by multiplying some kind of matrix with some vector, right? Operation. So quickly you'll get the signal back, right? You can easily recover the signal. Okay. This is a very elegant technique. And this L1 trend filtering that I'm showing, this is also nonlinear filtering technique. These filtering techniques are actually can be utilized as a pre-processing step, right? For example, you have some image where you want to preserve some of the high frequency components, okay? Or you want to maintain a trade-off between high frequency components and low frequency components. You can see in this objective function, this whenever you use some kind of quadratic optimization, quadratic function, or the least square function actually, or MSC kind of function mean a square error you want to reduce, then your signal will be over smoothed. That means, for example, you have some image, it's a medical image, right? Medical image, if you take a CT scan or MRI or CT scan specifically, okay? So you'll have some of the sharp, components or some kind of significant or high frequency components will be there, okay? In that case, if you go for, over smoothing your data using say MSC loss directly, then those high frequency components will be gone, right? So therefore, what people do, they want to maintain a trade-off, right? They club this mean square error with the absolute value error, right? This is absolute value error, and they introduce this, dx term. This d means the first order difference matrix or the second order difference matrix here, which will exploit the high frequency component of the signal. Okay, how it's exploiting? So when you have a signal, when you multiply that with some kind of first order, second order difference matrix, essentially what is happening is giving you the transition between each pixel element, right? If you have image, you can have a transition between each pixel images, okay, each pixel. So if there is sudden, from black region to dark region, if you are going, say white region you are going, or say from white to some kind of dark region if you are going, if there is a sudden transition happening between consecutive pixels, then that value will be dominant reflected here, right? So that's a high frequency component. So that can be preserved, right? So this is how people develop many techniques. These are, you can say, some kind of filtering techniques. Those can be utilized for pre-processing your data, right? Because you cannot simply use the frequency domain pre-processing techniques like low pass, high pass filters, right? there could be some noise components which will overlap in the there could be spectrum overlapping that happening between the noise component and the signal component. Okay, very difficult to separate them out. Therefore, people go for some kind of non-linear filtering technique. Okay, so TVD, as I was talking about, is TVD. This is total variation denoising, and you can see here this term is known as TVD term, total variation term. Okay. So what information it gives us? It gives us how much the signal changes between the signal values. Okay, if you take an image also, the consecutive pixel values, how much is changing? The magnitude of change are actually accumulated. That's actually called the total variation of the signal. Okay, so they utilize this TVD concept, total variation density concept, to in many applications, including signal denoising, signal reconstruction, okay, or say feature extraction. In many places they utilize this concept, okay, and they obtained a closed form solution of that also. Yeah, I'm showing you some of the performance, denoising performance here. Similarly, you can also develop some of the robust estimator-based signal recovery algorithms or denoising algorithms. Okay, so mostly in this talk, I'll be focusing on some kind of denoising or reconstruction algorithms. However, you can extend these concepts actually to some other domain also. Okay, so in almost all the cases, we have utilized the concept of convex optimization or optimization techniques that is running in the background. And towards the end also, I'll touch upon some of the machine learning or deep learning based methods, and I'll show you how the background mathematics can be modified or that can be optimized. Okay, this would be very much useful for research purpose. So in this case also, whenever you propose any cost function, cost function could be utilized for solving many problems. Okay, you have a loss part, you have a penalty part. Okay, like some constant part is there and one objective part is there, right? So when you club them together, it's called the cost function, loss and penalty part. And you can take different loss and penalty functions, including like this loss and penalty. When I talk about loss and penalty, these are nothing but some kind of distance, right? You understand distance. Distance means measure of distance. Whenever I talk about some kind of norm, L2 norm, L1 norm, say L0 norm, any kind of norm I'm talking about, that measure of distance, okay, metrics. So you can utilize those, metrics over here to get some kind of, some result here. So we have used this Hoover and Burry function. Hoover is actually function looks something like this. When you plot it, actually, if I go to direct plot of this Hoover function, L2 norm, it's just a circle, right? You can see in 2D, L2 norm is a circle because it's a least square problem. So similarly, L1 norm, it's like a rhombus, pointy surfaces are there, right? And Hoover function is actually a combination of L2 and L1. You can see here, you might be wondering how can I relate all these, norms which my problem, real-time problem, or the way the AIML problems that I'm handling. Try to understand what we're doing actually. We are essentially when you do the back propagation, whenever you do some kind of pre-processing of your data, okay, many times we try to, you have some expected value, you have some, estimated value, you try to minimize it. Now, mostly you go for some kind of least square problem. Okay. Many times the cost function also in, it has some, L1 norm problem, right? L1 norm part. Right? So, but L1 norm is not differentiable. When you go for this back propagation or weight optimization, L1 norm is not differentiable. So there are ways to handle it also, right? So I'll show you how to handle it. So so in this context, actually, we develop uh, you know, various signal recovery algorithms. Okay, these algorithms have some loss part, penalty part, and we utilize various fever function, loss functions, and we obtain different, we have implemented it for various applications, including biomedical signal denoising, image denoising. Okay, many applications we have gone through, and it's giving us good results. Similarly, we also developed some kind of measuration, minimization, problem-based, algorithms. Just giving you this idea. It's a very much useful concept. Just note down this measure and minimize this concept. Okay. Many times your optimization problem may not be exactly convex. Okay. So what people do actually, they try to get a measurized version of your non-convex function. They solve it iteratively, and they get some solution, and they keep on solving, or they keep on developing new surrogate functions. We call it some kind of measurized functions, and they keep on solving it. Finally, at some point of time, there will be some constants which will be satisfied, and you'll get some kind of global minima. Okay, that's how they handle the non-convex functions. Okay, okay. So there are ways to obtain the, if you have some non-convex or convex concave part actually, you can utilize the Taylor series expansion, first order, second order, and different techniques are there to overcome this problem. I'm not going through the math, rather I'll quickly go through some of the concepts directly. This is a very interesting concept called proximal mapping concept, right? I understand most of you might be thinking, for most of you, all these concepts may be new actually. Since computer science, people are more towards the algorithm development, or more towards the application side. Okay. However, what I thought actually, let's explore the maths behind it, or let's understand how does it work actually. Okay, how does, what is the background theory behind it? Okay, or if you will get accustomed with all these new concepts also, you can utilize the concept in your cost function or loss function. That can be useful for solving some real world problems, right? So this proximal operator, or sometimes we call proximal mapping of a convex function, h, okay, is represented something like this. Okay. So what it does actually, it tries to find out some solution u. Okay. You have some problem with there h here, h is a function. You try to minimize it. Okay. You obtain some u value which will be close to this x value. Okay. So maybe you might be wondering, where can I utilize it? Let me show you some problems, right? So let's say you have some minimization problem, because nowadays people are not, directly solving one loss function or cost function. They try to club many functions together. If you remember, like if you are working on some kind of image denerging, super resolution problems, okay, image super resolution, or some kind of hybrid kind of problem. So there you can observe the cost function or loss function that you are using. It involves many small functions, right? Or based on your requirement. For example, you want to increase the PSNR of a image, right? Sometimes you use MSC loss, sometimes cross entropy loss, right? Or different kind of loss, dice loss. Sometimes people use for this segmentation problems. So all these loss function or small subparts of the function can be clubbed together, and they can be assigned some weights actually. They can be assigned some weight to obtain overall cost function. Okay, or sometimes we call it hybrid cost function, and we solve it. We obtain our we get our problem done, right? So that's how people handle it, and these problems can be also solved using one technique called proximal gradient operator, right? So where does it come into picture, right? So the idea is that if you have some function which is a combination of small functions like gx and hx, and gx is actually convex and differentiable, but h is not differentiable. Like L1 now, L1 is non-differentiable, right? So how do you handle the L1 norm when you do the back propagation from the output layer to the input layer while updating all the weights, right? So then you can go for this proximal gradient method, right? So what it does actually, it follows the step descent algorithm that you can see here, x minus some no step size is there. Okay, then gradient of the this objective function. So they follow step descent sorry, gradient descent first, then they use the proximal operator on that. So proximal operator means they will use a threshold operator, and using that, this is called the forward backward splitting technique. The algorithms based on this concept of proximal methods can be easily boiled down to two-step algorithms, right? Very interesting techniques are there. So if you start exploring, you can explore a lot actually. This will be especially helpful for PhD students who are working on the on some domain, because so far I'm sure most of you have understood that deep learning or machine learning AI are not actually generic algorithms. They are data driven algorithms, meaning that whenever you change the data or so everything changes actually, everything changes, right? So data-driven algorithms, and if your algorithm is developed for a particular data set or for a particular input size of input, immediately you cannot utilize it or use the tool or model actually that you have developed for some different data size. That's one of the major limitations of this AI ML based algorithms, which was not there in the signal processing algorithms. Okay. So there is another technique called ADMM, alternative derision method of multiplier. It also follows some Lagrangian operator, and they solve the optimization problem, right? Okay. Let's skip some of the algorithms due to lack of time. Okay. So this concept actually I'm talking about sparse searching and compressed searching. So what they do actually, they use the concept of some kind of dictionary. Okay, they called something called dictionary. Dictionary is nothing but some kind of kernel. Okay, some kind of matrix. Okay, what they do actually, they try to represent the signal maybe 1D or 2D in sparse domain utilizing some kind of transformation, maybe Fourier transformation or say wavelet transformation or some kind of transformation. They represent the data or image or anything in the frequency domain, and they see whether the data is sparse or not. If it is sparse in that domain, they process it in that domain itself, right? And in the meantime, if you remember or if you go through the literature of this, compensation, a group of people, like including the Michael Ellard, they also worked on this dictionary learning concept, right? Dictionary learning concept means uh, the kernel that they were using to recover the data or to deny the data or image, that learner is the dictionary is learnable, right? They tune the dictionary elements based on the data, okay, by using multiple learning techniques. Okay, so the sparsity concept can be utilized in many applications, and there are plenty of algorithms are there like convex optimization algorithms, greedy algorithms like matching pursue, OMP. So many algorithms are there. I hope so. You might have heard about some of the algorithms, right? Okay. And regarding the regarding the application domain, you can go for certain algorithms depending upon the computational complexity, right? And the accuracy or the performance also. Okay. So what's next actually? Okay. So sparsity, you understand sparsity is the structure of the signal, right? In hidden structure of the signal that people exploited to get many recovery algorithms or denoising algorithms. But later on, people started exploring that all the signals, practical signals, are not sparse in some domain. Okay, there are certain signals are there which may not be sparse, right? Due to the noise components or the structure of the typical signal, it may not be sparse in some other domain, including the frequency domain or some spatio-temporal domain. Okay, it may not be sparse, right? So in that sense, what to do actually? Then people started exploring the deep learning concept or AI/ML tools, right? So in that case, people explored this variational autoencoding, generative adversarial networks, all these tools they explored. As you know, GAN is a very interesting tool actually. So generative adversarial networks, it has two parts, right? Generator and discriminator. Okay, both are neural networks. Both are neural networks. So generator is like a police and the discriminator is like a thief, right? The generator, what it does actually, it tries to generate a fake data. Okay, a fake data from some noise, random noise, and this fake data will be compared with some original training data, because the database which is the original training data, that information is with you. You can compare this fake data with the original data. Definitely, the discriminator, that this is a binary classifier which which can easily distinguish between the training or original data from the newly generated data or synthetic data. It can tell which one is real, which one is fake, right? But gradually over the time, it's a feedback system. Iteratively, the generator will be stronger and stronger, and at some point of time, the generator will generate some data which will be very close to the original data. Okay, so in that sense, the discriminator get confused. Actually, the discriminator may not be able to distinguish which one is the real, which one is the fake, right? So people started exploring all these concepts, and they work. This GAN, as the name suggests, is the adversarial network. Okay, and they solve many practical problems, including the generation of data, data augmentation, many applications like denoising. Okay, so let's come back to the maths again, like the optimizers in deep learning. So quickly I'll go through it. There are certain important hyperparameters all of you know already, like epochs, the number of times an algorithm runs on the whole data set, like samples, batch, learning rate. It's a very important parameter, right? Learning is a parameter that provides the model a scale of how much the model weight should be updated. Okay. It's very similar to the parameter that you used in the gradient descent algorithm, right? Like the step size. Similarly, you have a loss function, cost function. This is also a crucial part, and you have a bias also, right? So, so here also, why do you use this? Optimizers actually in deep learning. You use this optimizers in the back propagation actually. When you do the back propagation, so you try to update the weights. Okay, weights are nothing but some of the some values which are actually connecting the input to the output via some nonlinear path, right? You have some y equal to say wx plus b, some weights you multiply data and some bias term is there, and you try to understand which path, right? By doing the back propagation, by propagation, you try to understand which input parameter is mapped to which output parameter. That linear, non-linear, mapping you want to explore using this back propagation, and it's actually a optimization problem actually. Yeah, and you don't put in the means if I say manually nobody develop all these loss functions already have standard tools are available including the Adam, RMS Prof, all these tools are already available. So however for research scholars I would suggest that they can also develop their optimizer. Okay. Because all these AIML tools are heavily depending on data and data driven algorithms. So I'll suggest everyone they can also explore some of the loss function or cost function. They can develop by their own depending upon the application or the type of data they are dealing with, and they can solve it. Right? There are ways to solve it. So the main idea here is that there is a transformation of the large data to some kind of you know first order stochastic methods, right? So essentially, in the large scale setting, you have millions of data, right? Millions of dimension of these weights and biases are in terms of millions, right? So you want to minimize it. Okay? So that can be easily done using some kind of many algorithms are there like stochastic gradient algorithm. You can see and you have the Nesterov accelerated gradient energy. You have the additive gradient, ADA grad is there, right? So in all the cases, if you see, you are updating some weights. Okay, these weights actually you utilize in the neural network. So these weights are essentially connecting the lying in the path between the input and output. Okay, so you have weight parameters and bias parameters. These weights you update while doing the back propagation so that you can have a clear cut relation between the input and output that you want to decide. Similarly, you have a RMS prop algorithm also where there are different methods they follow to update the weights. So why so many learning algorithms are there? The reason is that people started to minimize the training time. Okay, without any issues with the or compromise with the uh, you know accuracy or other other metrics, right? So they try to minimize the training time. So therefore, they introduce the concept of momentum here, right? They introduce the concept of momentum here for the bias term or weight terms. Okay. So they utilize the first order momentum, second order momentum, and they develop many algorithms, including this ADA grad, ADA delta, RMS probe, ADAM algorithms, right? So that this is what I was explaining, right? You have some input layers, you have some output layer, in between you have hidden layers, multiple hidden layers are there, and these hidden layers are actually initially taking the some kind of random weights here, and you obtain some output here, propagating from the input to the output terminal. However, the output or estimated output doesn't match with the original output. That's why you try to minimize the difference between these two, right? The original or gold standard output and the estimated output. You try to minimize this difference, and that's how you update all these weights, right? So there, the optimization plays a vital role. Okay. So gradient descent we have already discussed. And if you see the mathematical model for or the some of the state-of-the-art algorithms, including this gradient boosted decision trees or XGBoost algorithm, or say any kind of decision tree or some kind of tree-based algorithm, bagging or boosting kind of algorithm, there also you have some loss part. You can see in the objective function, they have some loss part. They have some regulation terms. They try to minimize it. Okay. So they can utilize this ADAM or say ADAGRAD or let's say RMS prob, any algorithms they can utilize. But each one has some pros and cons. As I'm telling you, to minimize you know the loss function, you should be very much careful which optimizer you should be using, right? Okay, so let's come back to our contribution in the domain of image processing. Mostly, I work on the domain of medical image processing, specifically low dose CT technology, right? So there are two types of CT, computed tomography image. Okay, all of you know how the computed tomography works, right? You have some kind of transmitter receiver combinations are there. There is a sensor array that will be rotating at it, and it will take images from different angles. Actually, it will try to expose the object here. There will be beam of X-rays. Those will be bombarded on the patient, and you obtain the images from different angles, and they club them together to get some kind of CT image. So what is the problem here is that so the normal dose city they put lots of current actually. Okay, the flux is quite the value of flux actually quite large, so that may get cancerous cell on the patient, right? Therefore, what we are planning, instead of exposing the patient to a large current or a large flux, we can reduce the current values so that the patient will be safe, although the will compromise with the images. Okay, the CT images that we will get with the low dose CT, the low current flux values, whatever the images we will get, that will be a bit noisy, or there could be dependent noise or poison noise will be there. But we have deep learning, machine learning tools are there. We can develop our own algorithms to get back the normal dosity, okay, from the low dosity. That was the main objective. Okay, this problem is very similar to super resolution problem with some medical difference, right? Or you can say some kind of feature based difference. Okay. So there are different types of deep learning based methods are already there. So we have also developed some of the methods based on GANs, CNN. Okay, and we have explored many objective functions. Okay, like including the Charbonnier laws, perception, perceptual laws. Okay, and we have suppressed the signal dependent noise, including the photon noise in city images. Okay, and we have avoided the blurring effect of the reconstructed image by choosing the composite objective functions. So as I mentioned in the machine learning, deep learning, nowadays people are using the hybrid loss, right? they're not using a particular loss function. Like in segmentation problems also, you might have seen there is say dice loss and some entropy, many combinations they take with different weight values, clubbing them together, they call it hybrid loss function, right? And they get a very good segmentation result or some kind of classification result or say denoising result. Okay, they obtain. Okay. Therefore, the loss functions that you are focusing on, those are very much important actually. And how do you choose that? Actually, that you choose depending upon the signal structure. Whenever you start a problem, always focus on that. You know, try to understand what information you have in the signal or the images, right? So yeah, depending on that, you can easily decide which. So based on that, actually, you can decide which loss function you can go for, right? If you have some sharp transition signals or images, in the images there are a uniform shade is there or gray level is there. Sudden there is a transition of the gray level. That means it has some high frequency components, right? So that can be easily detected using some kind of you can preserve that high frequency component or low frequency components can be also preserved. Therefore, you have to develop some kind of deep learning based methods, right? So here also we have developed various methods, not the only one that I'm showing. This is actually a voxel sensitive attention based network. Actually, we developed. We have a generator. We have multiple discriminators, and the discriminators that we have proposed here, one is based on the wavelet based discriminator, another is based on special domain discriminators, right? And we have a voxel sensitive attention network here. And after decomposing the signal into low, high, low, or high components, so we can easily preserve the sharp, very high frequency components. We can easily preserve. Okay. So we have proposed some of the methods. Recently, also we presented one of the paper in ICAS, okay, ICAS 2025 in Hyderabad. That's one of the best conference in signal image processing domain, like worldwide, and it happened after say 50 years in India, right? So that's a very good reputed conference. There we presented one of our work, right? And so there are various architectural elements of the proposed model. We have generators, we have discriminators. Those are GAN-based problems that we introduced here, right? And in the deep network that you propose also, there is a stack of building blocks called stationary wavelet based residual blocks. Okay, so nowadays if you see people are trying to explore the traditional signal processing in the machine learning domain. Okay, because machine learning, that's a framework, actually that's a standard framework. Everyone now have understood how does it work, how to utilize the machine learning tools, right? But if you can fuse some of the signal processing concepts which are very strong signal processing concepts like time frequency analysis, or let's say widget domain analysis, or many tools are there actually. Statistical tools are there. If you can borrow the concept and utilize that in the image processing or the AI based methods, you can definitely explore a new domain, okay? Or you can have your own algorithm or the method, right? So that may work, okay, but I cannot give you guarantee because so far I think you are you have become pro in using all these AI/ML tools so far. I understand computer people are very good in that domain. However, no one can guarantee that okay, if I am using this data I'm getting say 100% accuracy. If I change the data set, there could be drastically reduction in the data in the accuracy or precision or recall. Okay, there could be anything can happen, right? All are data dependent algorithms. And yeah, so there has to be there are many things to explore actually. So what I can suggest, like to the audience, that uh, since you are developing some, hybrid kind of objective functions or loss functions, so try to develop some loss functions by your own, right? It could be wavelet domain, perceptual domain, say adversarial domain, or any kind of, specific signal processing domain uh, tools you utilize and incorporate that in the loss function and then plug these loss function together to develop a hybrid loss. Okay. Although computational complexity will be a little bit more, you can also reduce. You can get a very good result, and later on maybe you can optimize the parameters to reduce the computational complexity. Okay. So database also you for our work we use basically different types of database, including this myoclinic database and low dose CT image and projection database. We have validated all of our algorithms using these databases. Okay. And hyperparameter tuning also we use the Adam optimizer. Sometimes this RMS prop also works fine, right? Some of the quantitative results also we have obtained. We have compared them with state-of-the-art algorithms, and our proposed method, outperforms some of the state-of-the-art algorithms qualitatively and quantitatively. Okay. And this is just one method actually I am showing here. Due to lack of time, I cannot present all these papers, but you can go through some of our recently published paper to explore the ideas. Okay, so I would like to stop it here. Uh, and if you have any queries, anything you want to discuss with me, please let me know. Okay.
Yeah. Thank you so much, sir, for your wonderful talk. And you've also
Yeah.
talked about the importance of the mathematics behind machine learning and deep learning algorithms. So, as we are most of us using deep learning algorithms as a black box, so it's really important to understand the mathematics behind it so that we can enjoy and we can also design our own, for example, loss functions, right?
Yeah.
So,
Yeah.
thank you so much for giving us this idea, at least, I mean, inspiring us